welcome to my good old data structures crash course, where I'm going to teach you the basics of data, variables, and data structures in computer science. So, today we are going to be talking about what is data, especially in the course of computer science. Variables, which are essential for coding and using any sort of information in computer science, and finally data structures. So I'm giving you all the context, and then we're hopping right into what data structures are and what they are used for. And also, as a disclaimer, all the coding information here is given in C#, which is like kind of important. These data structures can be used across many different coding languages, but some of the nitpick details are specific to C#. So first and foremost, what is data? It is a term that will be thrown a lot in computer science, but data is essentially information. Any sort of information that you would want to keep track of, such as like, here's a number 12, that is data, that is information. Here's like Abby, which is my name, that's information. Or even something like true or false, that is also information. Within the realm of computer science, data is information that you receive from a user, information that you calculate or change that is used throughout the code. And sometimes that information affects how the code runs, such as functions where you pass in information and it does something with that information. And sometimes the code kind of branches off based on what that information is, such as like true up here. Sometimes code has different branches if something is true or something is false. So information is essential for the running of computer programs. And data is often stored in things called variables.
Excellent.
So variables in computer science. Variables are how data is stored in memory for later use. There's a whole bunch of variables within the realm of computer science, but here are some very common ones. So we start off with integers, very basic. It's usually shortened to int, and that is a solid whole number. It can include negatives, it just cannot include any decimals. That is an integer. We have things like floats, those can include decimals. Strings, which are, like my name in the previous slide, Abby, any words, any collection of like letters, it can include numbers. All that usually kept inside quotation marks. That is a string. And Boolean, shortened usually to bool, that is your true or false variables. Keeps track of that. And objects, which are more complex variables, but in essence, objects are like your building blocks to object-oriented programming, which is very common in coding these days. Objects are made up of two components, typically properties, which is data, and functions, which are actions. The properties of an object can be made up of any of these other types of variables or also other objects themselves. That the object keeps track of its own data and its own functions, and it does what it needs to do. Like take, for example, a car. The properties of a car could be like the year it was made, its make, its model, its mileage. All those are information about the car itself. And the functions of the car could be like starting the car, changing gears, or driving. Yeah, there are additional types of variables, but these are just the most common ones that you will see getting into coding and computer science.
Nice.
Questions so far on variables or anything so far?
I think I just need to get some practice examples of objects.
Yeah, they are usually things that require more than just like, here is one piece of information. Because they're lowercase, they're called primitives. These are like your primitive types of variables. They hold one thing and one thing only. Objects, usually you get into more complex things like I'm holding more than one piece of information. Like a string actually is an object. It holds not just one letter, but usually a whole collection of letters. There's another variable type called character, shortened to char, that is literally one letter. By all technicality, a string is a collection of characters. So it is more
Mm-hmm.
complex. It keeps track of all of its letters. And also, with string objects, you can do things with them, such as take out a certain amount of letters and have a substring, which is a small portion of a string. You can take all the letters and make them lowercase. That is a function. That is something you can do with the string itself. So a string is also a very common object that you'll encounter in coding.
Excellent.
Yeah, it can be something as simple as just like a sentence for an object, or like something probably as complex as a car that's like has all this different piece of information and has all these things you can do with it. But it
Mm-hmm.
keeps track of more than one piece of information. Next slide. So there are four main components of variables. Three of these are like really important in your typical coding realm, while the fourth one I'm giving you as a bonus. So here is how you would create a variable within your code. First and foremost, you have its name. So we have int number equals 12. The name here is the number. This is how we refer to the variable and are able to call it in later lines of code. So you don't always have to use like 12, 12, 12, 12. You can just call number. That is the name of this variable. Secondly, you have the data type. This is the kind of data that this variable holds. It's usually the very first thing you put before the name of the variable itself, and that dictates the kind of information this variable can hold. In C Sharp, variables are what you call tightly cast, which means once you have a variable with a certain data type, it can only hold information of that data type. So the number can only hold integer values and only integer values. And that's the kind of data it holds because that is the data type of this variable. Thirdly, you have the value. This is the actual data inside the variable. And as per its name, this can often change. The value of number here is 12. It is what goes on the right side of the assignment operator, which is the equal sign. So we are equating the name number to hold the value of 12 inside of it. And fourthly, as kind of a bonus, this is the location in memory. You won't often get it up here, but when you create a variable, it is created somewhere in your computer's memory and is held there, where a variable is stored while the program is running. This is important for data structures. I'll get to it when we actually get to data structures, but for the most part, you can neglect its location in memory. Next up, how do we actually use these variables in code? So say we have this program that you just like put in all this information about some like student, some high school students. We have 5 variables here, right? We have the name of the student, say his name is Bobby, an integer for his age, which is 18, grade, 12th grade, and you have the float here, GPA, 3.8F. So in C Sharp, to my memory, I don't know if you actually do this in other languages. I think C Sharp, maybe C++. When you designate a float, you have to put an F after it so the computer knows it's a float. Boolean here, can graduate equals true. So whenever you want to use any of these variables, you just call them by name. Console.writeLine, that just means like you are taking this, you're printing it out as an output for the user. And so name, you call the variable here. This is just a string, call the variable here. And when this runs, it gives this output with the student's name, their age, their grade, GPA, and can graduate is true. Very basic rundown on how you use variables in code.
Very
So
nice.
variables are very easy to declare and use. As you can see here, you put their data type, the name. Sometimes you usually can just leave it as that until you give it a value later on, but you cannot use it until you assign it a value. And variables, again, allow data to be reused again and again in the same program without having to constantly like type out Bobby or constantly type out 3.8F repeatedly throughout the code. And variables also allow for easy maintenance of code, as you only need to change the information in one place if you want to update it in the future. Declaring multiple variables in code is usually not that big an issue, especially if you have like one, two, three of them. Like we have three integer counts here, just values of 18, 124, and 46. It's really easy to just pull those variables and like use them and call them and whatnot, right? Create three variables here, we use them here, write them out to the console. It looks something like this. Pretty nice, pretty clean, pretty simple. But what happens when you have a bunch of counts that look something like this?
I don't understand why count 3 is 124.
That's a good question. Did I do something wrong? Yeah, that should be 46. I actually don't know why that's that. I think I changed something and then I didn't rerun it. But what if you have like in your program just a whole bunch of counts and you're expected to use all those counts throughout the program? Is it practical to have a bunch of different variables like this? Probably not. That takes up a lot of space in memory. There is a much better way to hold this much information inside a computer program. And that is where we get data structures. The handy dandy use of this wonderful thing called data structures.
Nice.
So what are data structures? So first off, foremost, they are a way to store and organize large amounts of related data. Like we had all of those count integers, they're all probably counting something, they're all probably related. We should probably group them together into one thing. Data structures allow for efficient access and modification of data. Say you wanted to access like one of those specific counts and you named it something weird, or you're trying to find and remember which one it is. It's not the most effective to go through. It's like, oh, is it count 15, count 16, count 17? It's way easier to just like be able to pull one piece of information from a data structure and modify it. And it also helps with memory management, because the more variables you have, the more space it takes up in memory, especially to have that many. And also, data structures are technically variables. They're objects. They're complex things that hold more than one thing. You'll see more why, but data structures have their own data type. They're their own. You can give them names. They have their own space and memory. So by all technicality, they are also variables. But data structures. Using data structures in code helps out a bunch. So let's take this example of like all the 18 different counts we had in the previous slide. If you use a data structure like an array, it takes this 18 lines of code and simplifies it down to one. Here we're just creating an array. I'll show you what that is in a moment. An array of counts, and we have all these different numbers from over here. And instead of having 18 different console.writeLine statements, we can have one where we just go through this list of counts, pull it out, we write it to the console, and it gives something like this. And as you can see, the code is much cleaner with using data structures, and it's much more succinct. And it would also be very nicer on memory to have just something like this, instead of having all this and constantly having to pull a bunch of different things from memory. So that's the great value of data structures. As we are talking about data structures, I will give you 4 examples of data structures tonight. First and foremost with arrays, which we saw on the previous slide, linked lists, and stacks and queues. These are just a few of the many different types of data structures, but to get you started, we'll just talk about these 4. So arrays! Here is how you instantiate or create an array. Typically you have the data type here that you want to store inside. Arrays are denoted by the square brackets, which you would put right after the data type you want to store in it. And then of course we have the name, and you can like create this and immediately put information inside of it, or you can just declare it as an empty array. Like this. Arrays are static size, which means they can only hold a certain amount of information, no more, no less. It does not change during runtime, and it stays the same and very stable. In memory, arrays are contiguous. All that means is that they take up like a bunch of neighboring space, and that is it. So let's say like with this array right here in the corner, this is an array with 3 elements. It'll take up in memory just like say 3 blocks in memory that are right next to each other, and that is the size allocated to this array. Arrays, and like the other data structures we'll talk about tonight, they can only store data of one type, and typically data of one type that is related, that you'd put together. In other languages like Python, arrays are able to hold multiple different data types, which is pretty cool. It can also get pretty messy. And something else you'll see with all of these data structures, the new keyword is required to create these data structures in C#. All that really means is that when you use the keyword new, is that you are setting aside space in memory for these data structures. And with arrays, there's two kind of things you have to keep track of: the indexes and the values. So the indexes up here, they're kind of like the address of these values within the array. One of my friends who was a tutor in computer science, his name is Kevin, and he explained arrays like a whole apartment building. And you have all the addresses of these apartment buildings are like 0, 1, 2, and you go up to that spot, and that is where you'd find like the value 12 lives at index 0. Value 68 lives at index 1. And the value 32 like lives at index 2. So the indexes are how you'd find the values within the array and pull them out. And because computers are wonky, they start counts at 0. So index for arrays will start at 0 and go out from there. So using arrays in code. We had this earlier where you create the integer array of counts and you just immediately throw in all these values into it upon creation. You can also like have integers of strings or any other things as long as everything is the same data type. And you can do something like this where you create the array, this string array of winners, the new string 3, and this 3 in square brackets tells you the size of the array. But you access the indexes in the array and you can assign them values like this. So pulling out the index 0 for this array size of 3, you can put this value of like Bobby Bobbertson into it, or like the index of 1, put Autumn Dawn, index of 2, we'll put Leah Williams in there. So that's adding data. You cannot add more data than the size of the array. Inside the array, you've already allocated like the space in memory for it. You cannot add more data or else you'll get like an index out of bounds error, and that just means you're adding more than this array can hold. Arrays are static size, they cannot fit more than what they are given to hold. Accessing data, like I mentioned here, you just give it the index and it'll pull out that value. With removing data, it kind of depends on what you are putting inside of the array. Some arrays cannot handle you just taking something out completely and giving null, which just basically means there's absolutely no information here. For primitive values such as integers, floats, you cannot give a null reference by just removing a piece of information entirely. That gives an error like this. Because null is technically not the same as an integer value. For things like objects, you can put things like null in here. Yeah, it's typically kinder for objects to be able to put null, because typically when you put an object in there, you are putting a reference to an object. And null is a reference, it technically means no reference. So when you put no reference in there and it's looking through references, it works out just fine. And once again, the size of an array doesn't change, you just have an empty slot if you make a value null or just it doesn't exist. Onward to linked lists. So with the other 3 data structures I'm going to talk about, they have the greater than, less than symbols. That's because these data structures have these things called templates, which means it's created to hold just about any type of data. So you fill that data type inside the greater than, less than symbols on both sides of the equation. So you have their data type linked list. We're making a linked list of integers. So we put that here as its data type. List nums is the name. And then we're creating a new linked list of integers. Pretty straightforward. Linked lists are dynamic. They're able to adjust their size according to the needs of the program. And of course, they can only store data of one type. In memory, linked lists are not contiguous. So the data for linked lists can be placed anywhere in memory, and it does not have to be right next to each other, which is pretty cool. And in order to do this, linked lists are made up of nodes that contain a value and a reference to the previous and the next node within the list. This linked list in C#, they are called doubly linked lists because they have a reference to its before and after. There are a few different types of linked lists just depending on the way the nodes reference each other. I don't remember the name of it, but I think it's just like a normal linked list. Only has references to the next node and not back. Doubly linked lists go forward and back, but at the very end, the next reference doesn't go to anything, and at the very front, the previous reference does not go to anything. But you also have things like circular linked lists, where the last reference, the next one, points to the very first, and then doubly circular linked lists, where the first one, the previous one goes to the end, and the end one's next reference goes to the beginning. So using linked lists in your code looks a little something like this. Of course, we have the declaration here. And with adding data, there are 4 different methods that you can use to add a piece of information. Add lasts, which adds a piece of information to the very end of the list. Add after, where you can specify another node and then add the information that you want after that specific node. So here we have add after. This is another function that finds the node of 52, and then we want to add the value of 12 after 52. And then you have add before, which kind of does the same thing as the last one, but you add the value before the node you find. And add first, which adds a value to the very beginning of the linked list. And with accessing data in a linked list, you have the find method, which I use here, which finds the specific node with the value that you place inside. You have the find last, which finds the last instance of the value you pass in, because linked lists can have like more than one of the same value within the nodes. And then contains, it just tells you if the value you pass in, say I'm looking for the value 12, it tells you if it's there or not by returning a boolean of true or false. So if I'm looking for 12, I'd put like contains 12. It'd look through all these. If it finds any instance of 12, it'll return true, and otherwise false. There are 4 different functions for removing data from a linked list. There's clear, which just straight up removes everything. Remove, where you pass in a value and it removes like that specific node. Here I have like remove the value of 12. It'd go through the list, find the first instance of 12, and remove it from the list. And then remove first, which does remove like the very first node, and then remove last, which removes the very last node of the linked list. Next on, we have stacks. As with the other ones, where I'm just making a stack of integers, stacks are also dynamic in size. They adjust based on the needs of a program. In memory, in C# specifically, stacks are contiguous. I think also in C++, where I learned about these data structures, they're also contiguous. That's because stacks logic uses an array underneath. So whenever an array is full and you need more space to put in more information, it just makes a new array, copies all information over, and you have more space to put in more information. And since an array, it has to have all that space and memory right next to each other. Again, they can only store data of one type. You put that one type inside the template space here. And stacks operate under this logic called last in, first out, also known as LIFO, that abbreviation. What that means, as you are putting information, say you put in 32, and then you put in 68 in the stack, you're putting in 12 in the stack, and then you put in 0. 0 is the last value to be put into the stack. And when you want to pull information from that stack, you pull from the top. So if you want to pull information, you pull out that 0 first, and you use that, even though it was the last one to go in. The professors I've had, they use the example of like the plates at a buffet, where they just like stack them on, and if you want to use a plate, you have to get one off the top. That's the logic that stacks operate under. So using stacks in code, the functions are different here because it's a different data structure than linked lists or arrays. Adding data, the function here is called push. You push new information to the top of the array. And then accessing data, you have the contains function again here, tells you if that value is within the stack. Peek, which takes a look at the first value of the stack, and it tells you what it is. So if I wanted to know what was on the top of this stack right now, I'd use peek, and then it'd return 0 for this stack. Again, it operates under the last in, first out. If you want to actually use that value, you would use the function pop, and it would pull that information from the top of the stack and let you use it. And since you remove the top of it, the new top is the value underneath it. And then removing data from stacks, again, you can use clear, get rid of absolutely everything. Pop, which I talked about, just removes the very top elements from the stack. Last in, first out, logic for that. Last but not least, we have queues. Queues, we have another integer queue here, number queue. This is supposed to say queues of integers here. Queues are also dynamic. They adjust based on needs of the program, stores data of one type. In memory, they are contiguous. They follow the same line of logic as stacks, where they are implemented using an array underneath. And instead of last in, first out, queues operate under the logic of first in, first out, or FIFO, as commonly called. It's very intuitive to, like, if you're waiting in line at a checkout and you're the first person there, you're the first person to get their stuff checked out. And using queues in code. Function names are also different with adding data. You have enqueue, onqueue, how do you say that? You have onQueue, where you add information to the queue, and new information is added behind the very first value that is added. Accessing that data, you also have the good old contains function, which tells you if that value is there. Peek, which takes a look at the very first element that is there in the queue, which was the first element put into the queue. It operates on that first in, first out. Yep. And then removing data from the queue also has clear. You use the function dequeue to pull information from the front. Where we use these cool data structures. So with arrays, you'd use these if you know the number of information that you want to hold on to. And that number does not change. It is fixed, and it's that. Arrays have the value of quick access to data. Anywhere inside of the array, you can easily choose that index and pull out a value. Practical examples, if you want to, like, a list of game scores, list of students in a class of fixed size, or even just list of color palettes, you can hold that inside of an array. Linked lists, they allow for fast insertion and deletion of data. These are commonly used in playlist editing, where, like, you have a playlist, you can move around the songs. Browser history navigation, where you can go forward and back while you peruse the internet. Stacks, these are best if you want that last in, first out order, such as when you undo steps in a program, like if I'm editing in Photoshop and I want to undo what I just did, that is what you'd pull. The last thing you did, you'd pull from the stack and it'd undo that. In things like parentheses matching for evaluating equations, you want to put all the first opening parent in a stack, and when you find the closing parent, you pull it out, see if they match. Cool. Or in things like solving mazes. I've done that, like, kind of recursion thing. You go through, if you want to undo, go back, you just pull the last thing you did from the stack. Queues, of course, that first in, first out order is the benefit of queues. And you use these in task scheduling for operating systems or programs. There's things like the printing queue, which I've had to fuss with so much with my computer or at work. And trying to print things out, and it just, whenever you want to print something, you add it to that queue, printer prints it all out in order. Or like in customer service systems, where the first customer in is the first customer you help out. So as a summary of everything we talked about this last half hour, we talked about data, how it's just information, variables, how they hold data in memory, and to hold large amounts of data, you'd use data structures. And data structures we talked about were arrays, linked lists, stacks, and queues. Any final questions on this cool presentation?
It's good, thank you.
Yeah, now you know all about the basics of data structures. Go forth and code your basic data structure knowledge.